Now, the modulus of elasticity of the concrete, we're going to take it to be 4,000. It's reasonable, kips per square inch. And the modulus of elasticity of steel, it would be more reasonable, if it's more close to the real answer, to be 29,000, but in order to make the numbers a little bit easier, let's just take it as 30,000 kips per square inch, okay? So we have concrete on the top, steel on the bottom. They are connected. We are assuming that this connection is perfect between the two things, right? And that's our cross section. Now, what we have is, this is a bridge, and let's assume that this bridge has a span. It's spanning as a simply supported beam. It's spanning, let's say, 60 feet. And it's carrying a uniform distributed load, including its own weight, which is 2,000 pounds per foot, or 2 kips per foot. Our objective is to find what? Is to find the maximum stresses in this material. So we're going to find, let's say, the stress in the concrete on the top. Let's call that the stress sigma A. The stress at the top of the concrete. That stress is the same anywhere here, like this, right? All along this top line, that stress is the same. We also want to find the maximum tensile stress in the steel, and that's going to happen in the lower part of the steel beam. So let's say we call that sigma B in the lower part. And I could get it somewhere else, but yeah, why not? Let's also get it, just for fun, on the upper part of the flange, and let's call it sigma C. That is, that's in the steel, right? Just on the highest part of the steel, just below the concrete. Let's call that sigma C. Let's find those 3 stresses. Now, when we talk about those stresses of course change throughout the beam as the moment is changing. So our first task is to decide on which location along this beam is the moment maximum and what value does it have. So we take a look at our beam, and that beam has 2 kips per foot over 60 feet, so the resultant is 2 times 60, which is 120 kips. That's the resultant of those loads. Therefore, these reactions, without having to do calculations, by just simply looking at it, right, are equal to 60 kips. The shear diagram, it's clearly like this. It goes from 60 to minus 60. And the moment diagram has a maximum in the middle, and it's like that. And this value here in the middle is equal to this area, because the moment here is 0 at the support, and over here is just the area under the shear diagram. From here to here, the distance is 30 feet. And so we find that this moment is 60 times 30 divided by 2, because that's the area of a triangle. And 60 by 30 divided by 2 is 60 times 15, and 60 times 15 is 900. So the maximum moment is 900 kip feet. Okay? So we want to solve for the stresses sigma A, sigma B, and sigma C at the location along the beam where the moment is 900. Okay? Now I'm going to erase that to give myself some space. You already have it, and you can rewind if you need. Okay? Now I'm going to erase this too. And I'm going to make this a little bit out of scale to make the calculations a little bit simpler for you to visualize. So here is the concrete. that's the steel. Okay? Now, as we discussed in class, previous lecture, the theory that we know how to apply only works along principal axes. And principal axes are always axes of symmetry, or actually, if you have an axis of symmetry, that's a principal axis. So this section is completely symmetrical about this line, right? That means that that's one principal axis. The other principal axis is always perpendicular to, well, in other words, principal axes are always perpendicular to each other, so that means that the second principal axis is horizontal. However, because it is not an axis of symmetry, because it's not symmetrical this way, we really do not know where is this axis, so we call that distance to some place, right? Well, you can take any references you like. I'm taking the top, and I call it y bar. So I need to calculate then where y bar is. This is my principal axis xx, and this is my principal axis yy. Okay, now I know that you guys would probably, well, I don't know, I suspect that you would prefer the organization based on a table, and so even though the table sometimes takes more multiplications than are really needed, I'm going to do it like that for the sake of organization. So I'm going to say this is maybe a little overkill, but anyway, better overkill than not. So I'm going to put the area, the modulus of elasticity, the area times the modulus of elasticity, the distances to the reference line, then the multiplication of AI, EI, distance to the reference, then the distance y bar minus the distance to the reference squared, then AI times EI, which is this column multiplied by this, which is y bar minus yi squared. This table, of course, looks exactly the same as the table you've done to calculate centroids before and moments of inertia, except that we're carrying this modulus of elasticity. This is now the I about the centroid, or the centroidal axis of each piece. And finally, here is EI times I to the centroidal axis. This column, if we want to use numbers, is column 1, this is column 2, column 3, column 4, column 5, column 6, column 7, column 8, and column 9. And I'm going to stop for a second to just go check that everything is in the field of view. And I can see that it is. Okay. So, now let's start. The first thing is the modulus of elasticity, EI, here is 4,000 and here is 30,000. Sometimes, in fact most of the time, it becomes more convenient to just take a factor out of them and multiply at the end by the factor. It'll be obvious what I mean. For example, if I make this EC relative 1, then this ES relative is just 30,000 divided by 4,000, which is 7.5. So instead of having to write 40,000 and 30,000, I just write 1 and 7.5. And I remember that whenever I get a flexural stiffness, I have a 4,000 scaling that I have to add, and hopefully it'll be very clear when we finish this. So my first area is going to be the concrete. So that area is 48 times 4. And so an area of 48 times 4 is equal to 192. Okay? If you want to be superbly detailed, you could even make a column 0 here, where you could put the size. And you could say this area right here is a 48 by 4. In case you want to check yourself later, right? It's 192. It has a relative modulus of 1. The next area is a 12 by 1, and therefore is 12. The next area is a 12 by 1, and therefore is 12. And the next area, why do I call it 1? It's not 1. It's half. And so, see, that's why it's good to put this stuff I wrote. These areas are 12 by half, because I said these plates were 12 inches by half an inch. I think I did that. Let me double check myself. By half. Well, it doesn't matter. I guess I'll have to do the calculations again if I have the numbers wrong here. But anyway, 12 by a half. So again, 48 by 4 is 192. 12 by a half is 6. Another 12 by a half is 6. Another 12 by a half is 6. The EI, the relative EI of the steel, is 7.5, 7.5, and 7.5. Now I have to multiply, let me get my calculator handy here. I have to multiply AEI times EI to fill this column, right? And so I get 192 here. I get 6 times 7.5, which is equal to 45. And so I get 45 here, 45 here, and 45 here. Okay, now the distance y sub I in column 4 is simply the distance from the centroid of each one of the areas to the reference line. Since I am choosing the top to be the reference line, then the y sub I for the first one is 2. The y sub I for the second area, which is the plate, is going to be 1/4 inch plus 4, right? So that's going to be 4.25. For the next one is going to be 4.5 plus 6, right? 4.5 plus 6. So it's going to be 10.5. And for the last one is going to be 4.5 plus 12, 4.5 plus 12 plus 1/4. So it's going to be 16.75, right? And so we have the column of the distances. Now we have to multiply column 3 times column 4, and so we get 2 times 2 is 4, 384 for that one, and then we get 45 times 4.25 is 191.25, 45 times 10.5 is 472.5, and 45 times 16.75 is 753.75. 753.75. Now we have to add columns 3 and columns 5. So if we add column 3, we get 192 plus 45 3 times, for a total of 327. And if we add this other one, we get 384 plus 191.25 plus 472.50 plus 753.75 for a total of 1,800 and 1,801.5. Okay? Therefore, y bar, that is the distance to the reference, is equal to the sum of the AEY divided by the sum of the AEIs. So that's 1801.5 divided by 327, and we get 5.51. Okay, 5.51. That means that this right here, the neutral axis, is at 5.51 inches from the top. Okay? That means the principal axis, again I emphasize, this section has a symmetry axis here, that's a principal axis. The other one is necessarily perpendicular, but because it's not an axis of symmetry, we need to find where it is. And in these calculations, up to column 5, we have located where it is. Once we know where this axis is, we can proceed to complete the table, which is to calculate the flexural stiffness. Notice that what we have done here is exactly what you've done many times before, except that the areas get multiplied by the relative E value. Now, we come here and we calculate y bar minus y, and so I'm going to say, okay, so we take, it doesn't really matter what the order you take here because it's square, so you can take yi minus y bar or y bar minus yi, because those numbers are always positive. So the first y is 2, so we get 2 minus y bar squared, and that's 12.31. So this becomes 12.31. We take y, which is 4.25, subtract it, square it, and we get 1.59. We take y bar, which is 10.5, subtract it, square it, and we get 24.91. And finally, we take y to be 16.75. Take the difference, square it, and we get 126.36. Okay? Now, column 6 gets multiplied by column 3. In other words, it's AEY bar. Remember, this is the parallel axis theorem, except for the inclusion of the I. So now I take, for example, 1231 and multiply it times 192, right? So 1231 times 192, 2,363.5. 2,300 and 63.5. 2,600 and 3.5, yes. Then we take 1.59 and multiply it times 45, right? and we get 85.5. Then we take 24.91 and multiply it times 45. 1,121. And finally, we take 126.36 and we multiply it times 45, and we get 5,686. 0.2. Okay. Now we need the moments of inertia about the centroidal axis of each one of our sections. In this particular problem, all our sections, that is, are rectangles. And we remember that for a rectangle with a base B and a height h, the moment of inertia about its own centroidal axis is equal to 1/12 of the base times the cube of the height. So for the first rectangle, we have 1/12 of 48 times 4 cubed, right? So we have 1/12 of 48 times 4 cubed for a total of 256. So that's the moment of inertia of this. Now, most engineers at this point would actually put 0 on this one and on this one, because this is going to be 1/12 of 12 times 0.5 cubed, right? So 0.5 cubed is 0.125, so you can see that this is tiny, right? So they would just spare that calculation, but anyway, that's what it is, 0.125. For this one, it would be 1/12 of 0.5 times 12 cubed for a total of 72. And this one is, of course, the same as the other 1.125. Now, final column number 9 is just the I, which has to be affected by the relative E. So we have that 256 for the concrete come here, or for material 1, and then 0.125 times 7.5. is equal to 0.94. So we get plus 0.94.